Alright, so this chapter 7, it's on flywheel design. You're going to perform flywheel sizing for the punch project, punch press project. And it even has, so I have examples in the notes about punch presses, like for your project again. So what are flywheels? Flywheels are kinetic energy accumulators, and they are present in rotating machineries. Although an equivalent to flywheels would be the everyday life experience driving a vehicle loaded on a road. Truckers do this all the time. When downhill, they accelerate to build up kinetic energy and have that available to go uphill if there's a hill in front coming. But again, flywheels are used with rotating machinery, and they store energy. They increase their speed and accumulate kinetic energy when there is excess of it, and they by slowing, the flywheel releases kinetic energy. I'm saying here they serve a purpose similar to accumulators in pneumatic or hydraulic circuits. So for example, this air tank or the air compressor with a tank, the tank serves to absorb the pulsing air that's coming from the compressor and supply it as a continuous flow of air at about steady pressure. And also, many compressors have this feature where there is a controller that maintains the pressure in the tank between certain limits, and there will be times when the compressor is not running. The air is coming from the accumulator from the tank. Without one, you can buy from AutoZone inexpensive tire inflating compressors. The air will come out in pulses, and that's not suitable for certain applications, say driving impact wrenches or driving die grinders. It will be fluctuation in speed of these tools. And likewise, hydraulic circuits, they have hydraulic accumulators. Similarly in function, you're driving hydraulic motors versus pneumatic motors, similar to pneumatic accumulator and pneumatic cylinders. But here, although it's a different type of accumulator, here's the example of a gravitational flush toilet, and you have a very small diameter pipe supplying when the valve is released and you're bringing the water is getting back into the tank. So that pipe is small in size and inexpensive, and it takes some time to fill the tank, and then when it's needed, during a flush, there is a burst of water coming from the tank. If you're to provide that burst of water through a continuously flowing pipe, you would need to have a large size pipe, and again, that will be expensive. You could see that in some commercial toilets. There's no accumulator. It's just the burst of water that's coming straight from the pipe, the pressurized water. Okay, so in engines now, so yeah, we discussed it. Here too, you can see going back to the compressor, air compressor example. Here too, you can see it looks like the fan of the compressor to cool the compressor itself, but also serves as a flywheel. So what it does is the flywheel smoothens the resisting load experienced by the motor, because the resistance to piston motion is and the load torque on the crank or shaft of the compressor is variable, and the flywheel smoothen that and makes it closer to even the way it's sensed by the electric motor. And you could use a smaller size electric motor this way, rather than without a flywheel. You would need to have you'll be either experiencing large RPM fluctuations in the whole system, or you might need a larger motor just to overcome those peak torques, peak resisting torques or low torques. In engines, I started saying you have this is the case of a single cylinder engine, and you can see the sizable flywheel. Here's the case of a multiple cylinder engine, and proportionally the flywheel is smaller. Just look at the thickness, it's much thicker here. So in a 4-stroke engine, there will be just half a turn out of 2 full turns that work is produced. So during that period, the flywheel is accelerating, and then the rest, during non-powering strokes, you have energy coming from the flywheel, and the RPM of the crankshaft will be maintained about or closer to constant by the use of the flywheel. Flywheel also takes the slider crank of the engine off its dead centers, the zero transmission angle configurations of the top dead center and bottom dead center. We define what's called coefficient of speed fluctuation of a machine as the ratio between the difference between the maximum and minimum angular velocity, could be RPM also, and the average RPM. Okay, so you either use radians per second in angular velocity or RPM. This equation holds as the same. And there are some recommendations here in this table on what what typical values coefficient of speed fluctuation should be for various applications. So machine tools, you can see here in general, punching and forming presses would be your case, rock crushers, agricultural machinery. For electric generators, the AC electric generator, the coefficient of speed fluctuation should be very small, because the frequency of the power produced by the generator, it's function of the RPM, and if you have fluctuations in the generator crank shaft, then you'll be the frequency would be fluctuating around a nominal value. Here in this country is 60 hertz, 50 hertz in Europe. Okay, so how do we calculate the desired moment of inertia of the flywheel to satisfy an imposed given coefficient of speed fluctuation? Well, you need to know the change in kinetic energy, delta E, between the flywheel and the shaft, the power source. And knowing this, we can state that this change of energy is the difference between the maximum kinetic energy and the minimum kinetic energy of the flywheel. Maximum was the omega is maximum, the RPM is maximum, minimum when it's minimum. Now introducing coefficient of speed fluctuation. Okay, and then never define omega. I said it's average angular velocity, but for convenience, we're just going to take it as the average of the minimum and maximum omegas. And with this, and use the coefficient of speed fluctuation, so what do we do? Expand this as shown, and then recognize this term as being the average omega, and then if we multiply by average omega, then we get finally or make use of the coefficient of speed fluctuation in this formula. So knowing coefficient of speed fluctuation, average omega, and the energy exchanged by the flywheel, then we can calculate the moment of inertia, the required moment of inertia of the flywheel. First example, punch press. We have the geometry of the mechanism, crank length, connecting rod length. This is assumed to be eccentric, although I explicitly ask you to consider an off-centered punch mechanism, the slider crank mechanism. We have the hole diameter, and we have the material thickness, and we have the ultimate shear strength of the material, and we know that it punches 100 volts per minute. Okay, so I'm saying here, use the principle of virtual work to find the resisting torque of the crankshaft as function of crank angle. And then to evaluate the average torque delivered by the motor, and here's it's given the average motor shaft speed. Crankshaft of the punch rotates 100 RPM, so there will be a reduction, belts, gears, we care less at this point, between the motor, which is rotating 1620 RPM, and the 100 RPM of the crankshaft. Also told when the punch begins, and what crank angle, and what assumptions we're making to make the problem easier to solve is that the moving parts of the punch press have negligible, the punch itself have negligible inertia. We're assuming all the energy storage to be in the flywheel, although the motor itself, the rotor of the motor, has inertia. We're neglecting any friction to apply principle of virtual work. We're assuming energy, input energy equals output energy. And then we were assuming that the motor delivers a constant torque independent of its RPM, which is not the case. We haven't covered the chapter on motors, but and it's there where we are going to see that most or power sources like motors and engines, they don't produce or generate the torque that is constant with speed. And we're assuming the material to exhibit the ideally plastic behavior. It's shown here. So very little elastic deformation. The punch touches the workpiece, and then the resistance to punching is well, it fluctuates linear from maximum to zero resistance that is forced to the punch, but the stress in the that is developing into the workpiece as the hole is being generated by the punch. So the shear stress, it's assumed constant and equal to the ultimate strength and shear of the workpiece material. Okay. All right. So how do we calculate the maximum force? The beginning of the punch would be the side area of the hole, circumference time of the circle times height of the circle times the ultimate strength and shear of the workpiece material of the stock. And we're going to approximate the ultimate strength in shear of the workpiece as being 75% of the ultimate strength in tension. This is the easiest to and usually available in catalogs. Okay. Linear variation of the punch force from maximum to 0. This occurs only between the start of the punch and end of the punch. There's negligible or no force outside that acting upon the piston, the punch. And so this is described by these piecewise continuous functions. So F max, and this is the linear variation going from maximum to 0 as theta goes from the corresponding theta is between start of punch and end of punch. So to these two value, start of piston or punch displacement of beginning of the punch and end of the punch, start and finish, there will be angles theta that correspond to those displacements. Okay. All right. So a description of the resisting force, and now we're going to use this force together with an equation for velocity to calculate the required that is the resistant torque at the crankshaft of the punch press. So we haven't done this. We have done this in before chapter 3. How is the punch stroke function of theta? This is the equation. Again, it's a centric mechanism, not your case. You're not going to use these equations. Crank angle, crank length, connecting rod length, and then the relationship between theta and omega. Velocity times time gives you displacement, like in linear motion. And then we take the time derivative of displacement of the punch to get the speed of the velocity of the punch, s dot or ds over dt. And then principal virtual work says that small increase in s or change in s, ds, times the force applied equals small change in theta times the torque at the crank. So ds, it's not here, but we know this from before. So ds times f is going to be d theta times torque, the crank, the resistant torque of the crankshaft. The input torque is that constant torque coming from the electric motor. Okay, actually this first piece of equation 7-9 is principal virtual work. So T times d theta equals ds times f, and with ds known from before, and doing this little change or change of variable. All right, so we have ds over d theta. By doing this multiplication, we ultimately state how, or the equation for t. Okay, so energy. This would be a function of theta, and using f, which is piecewise continuous, will result in a torque T. You see it here. That'll look like the curve in blue. So this is the resisting torque. Negligible when punching, does not occur. It's spiking, as you see, and then goes back to 0. The energy for one punch, one cycle of the machine, you get it through integration. So integrate the resisting torque as with respect to angle theta, and radians gets you energy. So unit wise will be Newton meters times radians. That's Newton meters also for work. Okay, so doing so, we get the average, the mean torque, and it's shown here as a constant line. And this would be the electric motor torque. We said that the electric motor is delivering a constant torque, which is an idealization, and it is such that with the use of a flywheel, the energy that comes during one full turn, negative 180 to plus 180, it's the energy to do one punch. So let's look a little bit more detail of the so I have here a magnification of the portion of the curve in blue, the torque curve, resisting torque curve, and the average torque curve. Okay, so before the punch begins, there's excessive energy from the electric motor, and that goes to the flywheel. When the punch, or during the punch, I have a little bit of energy delivered from the motor, but the majority of it comes from the flywheel, which slows down from the maximum RPM to the minimum RPM. Okay. So that delta E, in calculating in the early equation, calculate the required moment of inertia of the flywheel, this delta E is going to be, for this graph, is going to be the area above the red curve and delimited by the blue curve. Okay, I have let's see, I'm trying to magnify this, and again, the what's above the red curve and below the blue curve, it's delta E, also equal to what's below the red curve and delimited by the blue curve. So delta E would also be this area here plus this area here. Okay, that's the energy that goes to the flywheel. This is the energy that comes from the flywheel. But otherwise, this analysis allows us to calculate the average torque Tm, and if you know the crank speed, you can calculate the power required from the motor. Not that that will be exactly the motor power. You need an excessive power available. So if you calculate this to be 0.1 of a kilowatt, 100 watts, it doesn't mean that you will see on the punch press a bathroom fan size of a bathroom fan motor. Will be substantially bigger to accommodate for larger holes to be punched, and also to be able to accelerate quickly the machine from rest. Back to the trucker driving up and down the hill example, if or maybe you have driven a truck like a U-Haul truck, you know this very well, that if it's loaded, it takes longer to accelerate, and even harder to accelerate uphill. Think of in general of an application where it has to start under load, like a conveyor belt or bulk material transporter with an auger and stuff. Okay, so here I'm saying what the all right, so how do trapezoidal rule of integration? It was discussed in the chapter on forces, chapter 6. These come available as discrete points. You use trapezoid to get the area under the entire curve. You divide it by 2 pi to get you the average torque, and then you need to look at the magnified figure like this one to see where it starts and where it's ending, and to calculate the area above the curve, the red curve, and below the blue curve. Okay, so so I have this power in kilowatts. This corresponds to to the so you see here mean torque and RPM. This is how you get the power when you know the torque and you know the RPM. Both one came from calculation and the other one given. Okay. The actual sizing of a press flywheel. This is the case of for the numerical example, consider to explicit what the minimum and maximum, starting from coefficient speed fluctuating, what the maximum minimum RPM would be, and then the case of numerically or calculating the area of delta E that we discussed about earlier. Okay. So all this is stated in like integrals, but in actuality it would be a matter of determining sums of trapezoids and applying the equation that was introduced earlier. Okay, I mean it was equation 2, I believe. Okay, in addition to the working, in addition to the Excel part where you're going to do the numerical integration of find delta E and calculate the required mass moment of inertia, you're going to simulate the punch press in working model. I have here a screenshot, and you introduce the motor torque, you have the mass moment of inertia, at least the way I did that working model simulation. The maximum punch force, and using controls I can adjust the location of the workpiece. I have some reference points, and I have a reference point on the punch, and I'm using the formula language to determine where if the reference point on the punch is between the beginning of punch point and the punch point. So if so, I'm using this F max to generate the resisting force. I also have controls to adjust. You don't need to do this. The thickness of the workpiece, and in calculations I'm taking the motor torque and adjust it with the reduction ratio. Okay, so and then initial RPM, if you start from 0, it will be the transient. You're at the beginning. Clearly, when you start the press, you let it run for a few seconds to come up to speed, and only then you begin punching. You don't have the workpiece ready to punch and you flip the switch. That's may or may not work depending on the load. You may you may stall the equipment. Okay. And we're going to discuss this specific to the project. I'm going to project the my spreadsheet, and let's do it like right now, as well as the working model. So let me pause this while I'm bringing up the working model and the spreadsheet. Okay, so this is the way I organized my spreadsheet. I have some inputs showing in red input cells, and I labeled them. So R_2_3 eccentricity, the RPM. There are different values than in the sample problem, although I could customize it quickly. I have the shear strength, ultimate shear strength of the material, shear area, stock thickness, and when the punch starts. This is not given in terms of theta, but rather is given in terms of S. Okay. What's in blue are calculations. So I have omega. This is the based on the RPM of the crank. And then I have the calculated maximum strokes of the punch, and calculated average torque in Newton meters and average power. So using this RPM, calculate the average power. Okay. So yeah. So if I'm saying punch begins. Punch begins at 63, or at 0.634 meters. I'm adding the workpiece thickness H, and you will see where the S end. So I have start and end. I used F finish, S start, but I'm sure you can make sense of these easily. All right, and then in terms of spreadsheet organization, I have numbering and then time in seconds, theta going from time to theta 2 via omega. You just multiply t by omega, and then converting to radians to degrees. B and C to solve for S, the coefficients of that quadratic, A equals 1, B equals C. Again, this is up to where? Up to here is your homework number 4, was it? And then the remainder of the columns are for force. And then here's the principle of virtual work. So you just say force times delta S over omega, which is constant, gets you the torque. So how's force? Force is going to be constant less between the punch displacements where less between where punching actually occurs. Okay, so I have punch start and I have punch ends. I'm looking here, so S, this is the start of the punch. At the resolution of the points that I have, the finer the resolution, the shorter the time interval. And by the way, you can add points in the area of interest and make it finer time increment. So yeah, punch starts and it ends like right here. So these two values approximately, again, at the resolution of the allowed by the time step, which you can improve. Okay, so the force now, what I did, you can do it two ways. You can do it a very easy way. You just find where the punch starts. Okay, not a good color, so let's color it blue. I said red is for the input, and when the punch ends, the closest values. And then in between, you're just going to generate that equation from the notes, the piecewise continuous function for F, this one. Okay, elsewhere just populate by 0. So we're in between punch start and punch ends, punch finishes. You plot this you code this equation in the spreadsheet. So this is the easy way. The more advanced way is the way I did it. So I'm saying if the if the punch displacement is greater than S start and less than S min, I'm writing that equation with F varying linearly. Outside is going to be 0. So it's an if statement. This gives me flexibility. I can change when the start begins. I can change where the start ends. Again, accuracy is dependent on the time interval considered here. I'm taking 0.001 of a second. Could make it half, that is double the total number of points. I think I have 720 points, yes, but I could, nobody stops me to have 7,200 for added resolution. Okay. So yeah, that was the more advanced way to use the if function, and I have here the end function, so if function and end function for F. The torque, I said, is just principal virtual work. So torque is going to be force times ds over d theta, and it comes out to be also equal to so virtual work, also virtual power. You can write it as so the principal virtual work has an equivalent which is called principal virtual powers, and you just take torque times omega equals force times velocity of the punch. Torque times omega of the, that is angular velocity of the crank, equals force at the punch times ds over dt, that is velocity of the punch, ds over dt. Okay, and that's why I'm using here, so this is rather principal virtual powers, because you see me using ds over dt divided by omega rather than f times ds over d theta. Okay, so I'm not simplifying, in a sense, I'm not simplifying by dt in the earlier equation. What was it? Just one sec. So I had was somewhere, okay, here. So instead of simplifying by dt in equation 7, 9, I'm just using them as they are. So this will be ds over dt from the whatever column in spreadsheet, and this is actually 1 over omega. Okay. And then the last, it says traps here. So traps is going to be each of these is a trapezoid integrating under the torque curve, torque versus theta in radians curve. So I'm taking, what's the area of a trapezoid? It's going to be the two values of the, I'm at, say here, I'm at between k and k plus 1. Sorry, so k and k plus 1. So I take the, I'm at k plus 1, I take the t at k value, or the tk value plus tk plus 1 values, and then times the change in theta 2 divided by 2. You may want to refresh your memory how to calculate the a trapezoid. This is actually going to be a particular case of a trapezoid where I have it like so. So okay. So this would be theta k. This will be theta k plus 1. This piece here is torque at k. This is torque at k plus 1. So I have area of the trapezoid is going to be this distance plus this distance times the two together added times this distance divided by 2. All right. Okay, so back to the spreadsheet. And then all of these trapezoids, all right, so all of the trapezoid, most of them are 0, less when the punch occurs. I'm not saving. Less when the punch occurs. That what was in yellow. I could find it, or and then what? I'm adding them, and you see here the sum of trapezoids divided by 2 pi. That's the length of the cycle, gives me the average torque. So, and I use the average torque, calculate the required power in kilowatts, and then what else? I'm recording the maximum force, and I'm comparing the maximum force as it's programmed by this equation. Again, I'm not matching exactly the beginning of the end of the punch because of finite resolution of T. And this is the error, the difference between the maximum force as prescribed and the maximum punch force calculated using ultimate strength of the workpiece, and the one that I'm actually getting using not matching exactly on where the punch, so not matching when the punch start as prescribed to what's available on column G. And then there's some graphs that I have. Let's see, I have graphs for displacement, velocity, acceleration, same as the homework. And then there is the graph for where is it? There is a graph for the, got it. There is a graph for punch force as function of the crank angle. I can also produce the graph of the torque, as function of, which are similar images. So this is no longer F. I drag the column of values to plot the torque versus crank angle. All right, I'm closing this without saving, and I'm going to show you the working model. Now I know this. I need to move the recording screen. So watch here. There's a workpiece and it's anchored, and so I'm moving this to where you can see more of the plots. And so yeah, what we have here, the slider crank, this would be the flywheel, reading the moment of inertia read from here. If I click on it, it says initial velocity input 18. That's crank initial RPM 18, and then also moment of inertia input 26. This is this one, input 26. So this text box is input 26. All right. In addition, I have the mean torque read from a text box. Stock location, I can change it. If I make it 0.7, just watch the stock is moving up. 0.75, and then thickness of the stock, can change it. 0.04 doubles 0.02. Okay, and then the maximum force as calculated is input 33. It's going to be transmitted to so I have a force somewhere that this force is conditional. You can see, and with the project specifications, I took a screenshot where you can see this length equation. Of course, you'll have different body numbers, and point numbers, but is the same. So it's an if statement, and if clause, and it says if this point 16 is between point 22 and 23, then there is a force, the linear force varying with the difference between y of point 16 and y point 22. Otherwise, it's 0. So this will be the 0. Okay. So yeah, you can do the same, or you are going to do the same, but for your own point numbering and the body numbering. Maybe body will get it as number 3, but points probably not. Okay. So, and then I have the, if I hit run, and this is also transmission angle, by the way. It's plotting. How do I get transmission angle? Transmission angle is just going to be the rotational angle. Let me split, and if I make this 0, no, rather this one 0. Okay, so you saw how I did the crank. I used this rectangle and drew it this way, not vertically, although it appears to be mostly in a vertical position in our model. And then when plotting the transmission angle, all I did was to just plot the angle of rotation of this body. Okay. So angle of rotation of that body would be this angle, which we know is the transmission angle of the mechanism. So let me make this small. I care less about the transmission angle now. And if I hit run, why it's moving so slowly? Because I have here on the accuracy side, I switch from automatic to, you see it's probably 10 times the automatic. Okay, so I said 0, 0, 2 was it? In order to capture, if the step size, the animation step is too big, I may not capture, you know, one frame to be before punching starts and the next frame to be after punch ends, and I'm not capturing the interaction between the punch and the workpiece. When I said interaction, is the way I define it. Working model is not that smart to where it can, I've seen students trying to just force the punch through the workpiece. By the way, these bodies neither collide, so edit, select all, objects do not collide. They don't collide. It's not like working model. It's so smart and knows how the steel material behaves when a punch travels and gets forced through it. Okay, hope that's clear. So so if I hit run, it moves slowly, and you will see the force. Need to wait a little bit, and by the way, I'll have to pause this for maybe 15 minutes, and here's the force, and it went from max to 0. And this is how the crankshaft originally, when the simulation started, was at this value, and now it drops, and now it accelerates. If the average torque of the crankshaft is calculated correctly, this zigzagging will neither move up nor slow down. And then we can confirm the coefficient of speed fluctuation by just looking at the minimum and maximum values of the minimum maximum values of the crank speed. Okay, so in a correct simulation, I would have to or see this zigzagging maintained steady. The punch force is shown here. Torque versus crank angle is shown here, and I chose to edit the limits to where I'm seeing magnified just the significant portion of the torque plot. Okay, displacement, velocity, acceleration. Okay, so I have the third zigzagging, and as you can see, it stays steady. What happens if I, instead of this value of the moment of inertia of the flywheel, what happens if I put a bigger value? The amplitude of zigzagging changes. It's going to be less. For a smaller value, let's say only 4, maybe 4 is too dramatic, so let's say 500. I haven't practiced, or not recently. So you would see, you would see that it's accelerating, so it's catching up speed, more speed, and slows, and RPM drops more. That is, the amplitude of the zigzagging will be increased, equivalent to a higher coefficient of speed fluctuation. So, more speed right before the punch, more drop in speed right after the punch, due to the different moment of inertia. The other value, calculated value, the mean crank, it's going to determine whether the zigzagging maintains the same boundaries, or it's for too big of an average torque, zigzagging will be up. For a smaller value, means I don't have enough energy from the electric motor, I'm going to slow down until it actually starts moving in reverse. Okay, so I need to stop here. I'm paused. Okay, so I'm back. We're going to finish the chapter, discuss a few more aspects, and this will be it. So I'm closing this, I'm not saving. And okay, the rest of the chapters, several aspects discussed. One is to actually size the flywheel, and again we've been through this. So once you know delta E, and you can calculate the required moment of inertia for a given coefficient of speed fluctuation. I used not the final formula with but rather the 7.2, the second equation, and then it's a matter of actually designing the flywheel. So you want to, of course, limit the size to the space available. You also impose a diameter of the shaft to which is attached. Here's what's called a parametric drawing, so all its function of the diameter, and there's an unknown, that K, the multiplier that gets the maximum outside diameter of the flywheel. There are 3 cylinders, one inside of each other, concentric. Total moment of inertia will be the moment of inertia of the individual cylinders. We have the density of the steel material that's used, could be iron, cast iron, by the way. And for a cylinder mass moment of inertia, it's an equation available on all dynamics books, or if you search online. And again, ultimately, you can follow the explanation. Ultimately, you're calculating K, constant K, and then the corresponding mass. It's pretty sizable. So it's over 1 ton, 1.3 tons, metric tons of metal. That's a bit big, and this is because it's placed on a slow moving shaft. Later in the chapter we're discussing the possibility of having the flywheel placed on a faster moving shaft, like on the motor shaft rather than on a crankshaft. If it's on the crankshaft, the advantage, you saw the disadvantage, it can be too big, but the advantage is that it protects, you know, all the impacts coming from, and fluctuation coming from the resisting force, the punch, are not delivered up towards the motor. So if there's a gear transmission, that's going to be protected by the heavy flywheel. If instead the flywheel is mounted on a motor shaft or an intermediate shaft that's rotating faster, then it will end up being smaller, and we'll look at the equations for that equivalence. Another example with a poppet valve Schramm compressor. I'm not going to go into details. So starting with the resisting force to the piston, derived from thermodynamics considerations, steps then become about the same as for the punch press. You know the pressure. You can convert pressure on the piston to immediately into force upon piston by just multiplying with the pressure with the cross-section area of the piston, and you get the torque. Again, this is a controlled valve, not one that's open due to the pressure difference and overcome the resistance of a spring, but it's rather controlled. So you likewise integrate under the torque crankshaft, crank angle curve. You get the average torque, and you find the moment of inertia. That's required to satisfy a given coefficient of speed fluctuation. And of course, the average moment of the motor, in these analyses, again, we are always assuming that the motor delivers a constant torque, irrespective of the RPM of the motor shaft. Okay, equivalent moment of inertia of a gear drive flywheel. So if we, and not only, could be a belt transmission, by the way. So if you have a gear pair, N1 and N2's number of teeth, R1 and R2 are pitch radii, okay, and you have an input torque and input RP or angular velocity, and then it's loaded by a resisting torque T2. As you can see, it's opposing motion here. Torque is in the direction of rotation, and motion of the shaft is inverse because of gear transmission. So this is omega 2. Okay, I have two moments of inertia. The entire shaft, you can include everything you saw earlier. You just add moments of inertia. They are concentric moment of inertia of the actual flywheel, but also the shaft itself and the gear has some moment of inertia. So total moment of inertia, shaft 1, I1, shaft 2, I2. What happens if I'm to take this inertia and replace it, add it to this faster rotating shaft, or vice versa? If I take this flywheel and for equivalent effect, overall effect, I take it and place it on this shaft, it cannot be the same moment of inertia. You have to account for the reduction, for the increase in speed between depending on which direction we go between these two gears. So here's a free body diagram showing the gearing force, just the torque generating force, not the radial forces. We know those exist, and we can solve the problem two ways. We can do dynamic equilibrium, right dynamic equilibrium equations with some moments about the axis of rotation of the first shaft, some moments about the axis of rotation of the second shaft. The gearing force is the one that's coupling the two equations. So Newton's law for rotating body, sum of moments is mass moment of inertia times angular acceleration. And again for the second one, okay, I said Fg is the the tangential gearing force. We know transmission ratio is between the two shafts. I12 is inverse of the number of teeth, inverse of the pitch radii or pitch diameter, but we have radii here because they occur with FG, and it's equal to input omega over output omega, and acceleration follows the same ratio. Okay, so eliminate tangential force between the two equations, and we go back and substitute it into I think it's should have been so 32, and we substitute in 33. I'm making a correction, and so we work the equations, and we want to essentially have an equivalent to I term multiplying, like in Newton's law for rotating bodies here, to have an equivalent moment of inertia, and we identify this indeed as the equivalent moment of inertia. So as you can see, if you go from the shaft 1, the input shaft, to the output shaft through the reduction there, n will be n2 number of teeth of gear divided by number of teeth of pinion squared. So this flywheel taken from the shaft 1 moved to shaft 2, I need to amplify the moment of inertia by the transmission ratio squared. That is squared. So if I have a transmission ratio of 2, I need to make the flywheel 4 times bigger. And I can repeat the analysis and find the equivalent moment of inertia of a flywheel placed on the fast rotating shaft. In that case, I'm making so if I take this to place it here for the same overall inertia properties, I need to make this moment of rather transmission ratio squared times smaller. Okay, so see the division here. Maybe this should be like a separate paragraph. So I'm pointing to the equations, but they were derived from energy considerations. So alternative to doing free body diagram and eliminating a gearing force between the two, you just say kinetic energy of the assembly, and then you say kinetic energy is equivalent moment of inertia times either omega 1 square or omega 2 square. It gets us the equivalent moment of inertia. But the conclusions are the same. It will be the transmission ratio squared that either needs to increase by that amount or decrease by that amount of flywheel that goes between a fast moving shaft to a slow moving shaft, or from a slow moving shaft to a fast moving shaft. Okay, and finally, this section, equivalent moment of inertia of translating and rotating masses. I usually ask in class if anybody knows somebody who has taken the flywheel off their vehicle and replaced it with a smaller flywheel. And this analysis shows that it's equivalent to essentially taking mass off of the entire vehicle. Everybody knows if you're driving an empty vehicle, you can accelerate faster. Not that you can drive top speed, steady state speed. It's not affected much, maybe by the or rolling resistance, which is function of the weight. But otherwise, maximum, and who's getting to their maximum speed their vehicle is capable of anyway. But in terms of accelerating properties, if you're replacing the flywheel on the crankshaft with a smaller one, it's like driving the same engine, a lighter vehicle. It comes with some problems. You're going to transmit the fluctuation of torque from the crankshaft to the transmission at a high, so that fluctuation will be sensed at the higher level, and it can have detrimental effect upon the endurance of everything that's downhill or from the flywheel to the wheels. Okay, so using energy consideration, we're having I'm stating here we're having a entire vehicle mass m. We have the engine flywheel moment of inertia IE. There's inertia to the wheels. There's inertia elsewhere, but we know how to take the rotating masses and move the equivalent inertia to the engine by just multiplying by, or rather dividing by the transmission ratio square, the transmission ratio inside of the transmission. So this is what exactly this equation says. The kinetic energy is going to be the kinetic energy of the engine flywheel, kinetic energy of the four wheels, assuming all four to be identical, plus kinetic energy of the translating mass of the vehicle m. Okay, so we can either say, let's make, and we can relate velocity of the vehicle to the engine RPM or omega by involving the radius of the wheel in a transmission ratio. So it's what this these two equations say. So the total transmission ratio is transmission ratio of the transmission and of the final drive. Okay, and then velocity of the vehicle is angular velocity of the wheel times the radius of the wheel. Okay, so with these findings, we have the equivalent kinetic energy as being the equivalent, or rather the moment of inertia of the flywheel and the crankshaft plus moment of inertia of the wheels. Okay, and then I switched from 4 to 2. I don't know why I did this. So this has to change. If I'm taking 4 individual wheels, or I could take just this wheel and its pair plus the transaxles. Anyway, so the equivalent moment of inertia, as you can see here, at the flywheel, at the crankshaft lumped with the flywheel, is going to take the mass of the vehicle and amplify by the radius of the wheel square and divided by the total transmission ratio square. If instead I take mass off the flywheel and see how it's going to influence the equivalent effect upon the translating mass of the vehicle, you can see here it's is going to be, transmission ratio squared and divided by the radius squared. So the what we discussed earlier, like reducing the inertia of the engine flywheel, is equivalent to taking this much mass. The equivalent mass would be this one that you take off the vehicle. Okay, we can play some scenarios. All we need to know, like, what is the maybe say a 10% reduction in moment of inertia, transmission ratio in the first gear when you start accelerating from rest. Like total transmission ratio could easily be 16, so you have 16 squared, and then the radius of the wheel square, maybe half a meter radius. So again, you can judge qualitatively based on this equation what the effect is. Again, it's squared of transmission ratio and radius of the wheel. I'm going to solve some problems with you in a different recording using my cell phone as a camera, but I guess this was this chapter on flywheels, and you pretty much have all the information that you need to complete part one of the project report up to selecting an electric motor for your punch press. Okay, so this being said, I'm going to stop recording. Thank you for watching.